Hello, welcome to Soft Papers channel. I am Godfrey. In this video, I am working out Cambridge A2 physics questions. Topic is gravitational field. These are questions that were set on 2019 June. I encourage you, every time you are preparing for your exams, like forthcoming exams 2021, I encourage you to revise, to do your revision topic-wise. Read a given topic, and when the content is fresh in your mind, attempt questions that were set on that particular topic for a number of years. And this way you will get to know the key areas of that topic that are frequently tested. And once you're done with the topic revision, then you can now resort into past papers and do full past papers. Of course, you can time yourself to build speed to see whether you're measuring up. And in that way, you will prepare adequately for your exam. You don't get flat-footed. If you have not already subscribed to my channel, please click the subscribe button and hit the bell icon. This way you will be notified every time I upload a new video. May we get started? This question, the question number 1 that you are tackling here, was set on paper 4.1, variant 4.1, and it was question number 1 of May-June 2019. You'll always can refer to that past paper or your marking scheme is so wish by looking at here. You'll be guided where the question was, which variant the question was set, and what question that was. I hope that will be of help. It may get started. Question number 1. 2-point masses are isolated in space and are separated by a distance x. 2-point masses. Okay. State an expression relating the gravitational force F between the two masses to the magnitudes m and m, which are masses. State the name of any other symbol used. Of course, this is the equation that we all know too well. The equation is F, that is the gravitational force F, is equals to gravitational universal gravitational constant G times mass of one of the point masses times the mass of the other, and this is divided by the separated distance squared. Of course, you can specify this by saying where F is gravitational force. Of course, it is stated here. G is the universal gravitational constant. Universal gravitational constant. Of course, x is the separated distance we're given there, separated distance, and of course m are the masses which are stated there. So the state the name of another symbol used. This is the one you needed to, which is not provided for in this statement. Part B. A spacecraft is to be put into a circular orbit about a spherical planet. The planet may be considered to be isolated in space. Isolated means that it is not under influence of another neighboring particle in terms of gravitational attraction. The mass of the planet assumed to be concentrated at its center is this, 7.5 times 10 raised to the power 23 kilograms. The radius of the planet is this. The spacecraft is to orbit the planet at height of 2.4 times 10 raised to power 5 meters above the surface of the planet. At this altitude, there is no atmosphere. No atmosphere basically means no air resistance. No air resistance at all. Show that the speed of the spacecraft is this we are supposed to show. when you're taught to show, don't fake, and just do it the right way. When we are marking, we always follow your workings. You don't just mark the answer because you're given the answer already. So here, since it is in a circular orbit, this spacecraft is acted upon by a centripetal force. A centripetal force is in action here. Okay, and we know that this is due to centripetal force is due to the gravitational force is due to gravitational force, which you have said F is equals to gmm over x squared. We know that the formula for centripetal force is mv squared upon x, of course, which is r, and of course the gravitational force is equals to gmm over x squared. Therefore, since centripetal force is due to the gravitational force, then we can equalize the two forces because they are equal. Mv squared over x is equals to gmm over x squared. Of course, this m will cancel that m, and one of the x will also cancel. This x will cancel here to get x, and therefore what we'll remain with here is v squared is equals to gm over x. We're supposed to find the speed, so the speed will be equal to square root of gm square root of gm upon x, this formula here. So we know the value of the g, so speed is equals to 6.67. You can get this from your data in your question paper. Minus 11 times the mass is given here, 7.5. 7.5 times 10 raised to power 23, and we are told the radius of the planet is this. Of course, if you are to get the planet here, if this is the planet, we draw a smaller one. This is our planet, right? The spacecraft is orbiting at a height of this. So, assuming that is the height at which the orbit is occurring, then we know that the distance from here to here, this is radius, but the distance from here to here, this is x, right? And our x is equals to r plus the height. R plus the height, plus the height at which height of orbit. Okay, so then of course here we get the radius, which is 3.4 times 10 raised to power 6, plus the height is 2.4 times 10 raised to power 5. Okay, we need to be keen of that, and then of course you're going to get the square root of this, square root of all that, and use your calculator. If you evaluate this correctly, you're going to get 3.7 times 10 raised to power 3 meters per second, which is what we were supposed to show right there. Part 2. One possible path of the spacecraft as it approaches the planet is shown. Okay, this is the planet. This is one possible path as it approaches that. This is not drawn to scale, not take of that. The spacecraft enters the orbit at point A with speed of 3.7 times 10 raised to power 3 meters per second. At point B, a distance of 5 times 10 raised to power 7 from the center of the planet, okay, this distance here, the spacecraft has a speed of this. The mass of the spacecraft is given as 650. All right, that's the mass of the spacecraft there. For the spacecraft moving from point B to point A, show that the change in gravitational potential energy of the spacecraft is 8.3 times 10 raised to the power 9 joules. Okay, we are supposed to show that. And to show that, you use the equation for potential energy. You know that potential energy, this one here, is equals to minus gmm over x. And we can get the gravitational potential energy at A, which is of course going to be, use this equation, 6.67 times 10 raised to the power 11 times the mass of the planet, 7.5 times 10 raised to power 23 times the mass of the spacecraft, which is 650. Of course, the distance between the planet and point A is 3.64 times 10 raised to power minus 6. Of course, 3.64 is given right here. 3.64 is given right here from the center of the planet to the orbit, or the height where A is at. When you work out that, this you'll get as 8.93 times 10 to the power 9 joules. Then now you can find GPA, gravitational potential energy at point B. Same thing, 6.67 times 10 raised to power minus 11 times 7.5 times 10 raised to the power 23 times 650, 650. The distance x, for this case for B, is indicated right here. It's 5 times 10 raised to power 7. That is the distance you use. Here, 5 times 10 to power 7. When you evaluate correctly, you get 650 times 10 raised to power 8 joules. Therefore, the change in energy that we are supposed to find, show that the change in gravitational potential energy, the change in energy is energy at A, which is greater, you can see, minus energy at B. Therefore, the change will be this 8.93 times 10 raised to power 9. Take away this 6.50 times 10 raised to the power 8. When you do your correct evaluation, you'll get 8.28 times 10 to the power 9, which is approximately equal to 8.3 times 10 raised to power 9 joules, what we were supposed to show right there. Part C. By considering changes in gravitational potential energy and kinetic energy of the spacecraft, determine whether the total energy of the spacecraft is increased or decreased in moving from point B to point A. Numerical answer is not required. Of course, you can see the speed given here. The speed is, we're told that at point B, the distance that, the speed is this, 4.3 times 10 raised to power 3. And we know that the speed at A, which we had calculated here, we are to show that the speed of the craft is this, 3.7. So the speed has decreased. So if the speed has decreased, then kinetic energy has decreased as well. And potential energy has also decreased, because at point B, the potential energy is this, and point A, the potential energy is this. So the kinetic energy has decreased, and the potential energy has increased. Sorry. So you can say that kinetic energy decreases. So if the kinetic energy is decreased and potential energy has decreased also, potential energy has decreased. We are supposed to gravitational potential energy, by considering the changes in gravitational potential energy, determine whether the total energy of the spacecraft has increased or decreases from moving from B to A. So in this case, you would now say, so the total energy has decreases as well. Okay, we are supposed to what we are supposed to do, determine. All right, remember, okay, I need to remind you this. Remember, GPE is a negative value. It's minus GMM over X. So when you consider this is minus 8.93 and this is minus 6.65, then this one is greater than this one because it is a minus. So that's why we say that the GP has decreased as well, moving from B to A. So the negative sign indicates decrease. GP is greatest at infinity, and either at GP is 0 at infinity. Remember that 0 is greater than any negative number. All right, so what you are saying is that minus 8.93 times 10 raised to power minus 9 is less than minus 6.50 times 10 raised to power 8 joules. So the energy has decreased. So take note of that. So the overall, the total energy has decreased as well. Number 2, before we get on with number 2, it's great you're watching this video, but remember, practice makes perfect. I encourage you to practice working out the questions yourself as I guide you. So as usually is the case, you may get the same questions that I'm working here right now from solvedpapers.co.uk. The site I'm referring to is this one. This is solvedpapers.co.uk. You need to go here. Physics, of course, you can get mathematics, chemistry as well. 2019, of course, A2, you go there. That is where what we are dealing with. The paper we are dealing with now is June. Of course, you can get November and June topicals. This is not to say you don't need to do past papers. You can also get past papers as well. But you're dealing with June now. You go June. The paper you're dealing with is Gravitational Field. Of course, you need to click here to get all of this in a zip folder. Of course, when you click here, you'll come to this page here, 2019. You come down here, June. So this is the paper I need you to click. You click here, and you may request your parents to assist you in acquiring these papers. Only £10, well priced, and you'll get all the topicals in June. And I encourage you to get as many topicals as you can. You can get June and also get for November 2019. You can also get 2018, same November, and also June as well. 2017 as well and 2016, or you can get all of them at a discount. Of course, you get at these discounts, you can ask your parents to consider going for the discount. That will make them save a little bit. Still, when you are at that, let me also mention that if you need some help online, I also do help students online. I also do online tuition at this site as spaceacademy.speacademy.co.uk. You can give it a visit. The site I'm referring to is this one, SP Academy Software Pass Academy. Of course, you can take time to explore the site here. We do offer ICT, mathematics, physics, biology, and chemistry. And I need you to have a look at the student guide on how to set up your own account. Step-by-step guide is available here. You may also have a look at the video to get familiar with the online classes. And once you make up your mind, then you need to register. You can just click over here. Then you will you'll be taken to this page over here to register. Once you do your registration, of course, we will send you an email to activate your account. How to activate your account? Once your account is activated, then you can log in. You see your password and your username. Then you can click over here to find a tutor. And I will help you if you so desire. You may also want to know if it's one-on-one. I'll only charge you £35 per hour. If you come with your 3 friends, so that you are 4 or even 5, then I'll give you a discount of £10. I'll charge you 25 pounds per hour. So give me a try and let me help you get your A star in physics, and you'll be happy a lot. Question number 2 was set on paper 4.2, and this was question number 1, May-June 2019. All gravitational field questions are usually the first one in every given topic. So we are told, part A, 2 point masses are separated by a distance x in a vacuum, no air resistance. State an expression for force F between the 2 masses, M and M uppercase and M lowercase. State the name of any other symbol used. Of course, force here is usually a gravitational force between 2 point masses. Is usually a universal gravitational constant times the masses of the 2 point masses divided by the square of the distance that is separating. And therefore, we are given F is the gravitational force. These are masses, and this is the separate distance. And we are taught to state the name of another symbol used. So the other symbol used that is not stated is G, and G is what we call universal gravitational constant. So that will earn you that 1 mark. Let's go to part B. Part B is a little bit lengthy. Be patient. Small sphere S is attached to one end of a rod. Small sphere is this one here. It's attached to an end of a rod as shown in fig 1.1. This fig here, which is not drawn to scale. So it is attached right there. And the rod is suspended on a thread. The small mass is 8 centimeters from where the thread is. Of course, since this rod seems to be balanced, then at COG, that is where the weight of the rod is balancing, and therefore the COG should be some distance x. If you know your moments from AS, So this is viewed from side. The rod hangs from a vertical thread and is horizontal, meaning that it's balanced. The distance from the center of the sphere S to the thread is 8 centimeters. A larger sphere L is placed near to sphere S, which is suspended on the rod and the string like that. Is shown in Fig 2, right? We have here. So this is a large sphere L, which is 6 centimeters from the smaller sphere here, all right? And then, of course, you can see the rod has rotated. This was the initial position of the rod, and the rod has the final position here, which has rotated a distance of 1.2 millimeters of an arc. Of course, there's the radius, there's an angle there. Of course, the distance remains the same. So this is viewed from above, and it's also not to scale. Take note of that. There is a force of attraction between spheres S and L, causes sphere S to move through a distance of 1.2 millimeters. The line joining the spheres, the center of sphere S and L is normal to the rod. Show that the angle through which the sphere rotates is 1.5 times 10 raised to power 2 radians. Right, so we're told the line joining the centers of sphere S and L is normal to the rod. So if it is normal, then we know that the angle in radians is usually equal to the length of the arc over the radius. Okay, so that is the radius of the circle. All right, so we know that angle in radians is equals to length of the arc over the radius. Of course, you know this from this equation. Theta is equals to S over R. Of course, we know that the length of the arc is 1.2 millimeters, which is 1.2 times 10 raised to power minus 3 meters. And the radius of the arc, the radius of the rotation, we are given right here, which is the radius of the rotation, which is the radius of the circulum. If you are to continue this one and be a circle like this, then the radius is 8 centimeters right there. Therefore, that is what you need right here. So that is what we need right here. So times divide by 8 times 10 raised to power minus 2 meters. Don't forget, milli is 10. Milli is 10 raised to power minus 3, and centi is 10 raised to power minus 2. So that's what we do. So that will cancel out. Meters will cancel out. And what you'll get is 0.015. And this is radians. Of course, you convert this one to standard form. This is 1, 2. So this will be 1.5 times 10 raised to power minus 2 radians. We have showed that. Okay. Part 2. The rotation of the rod causes the thread to twist. The torque T in Newton meter required to twist the thread through an angle of beta in radians is given by this. Torque is T. Torque is equals to 9.3 times 10 raised to power minus 10 times this angle in radians. Calculate the torque in thread when the sphere L is positioned as shown in Fig 1.2, and therefore we're given this to be in radians. We have calculated here, we have shown it here. So then, of course, to calculate the torque will now be equal to 9.3 times 10 raised to power minus 10 times the angle in radians, which you have calculated, which is 1.5 times 10 raised to power minus 2. And correct evaluation will give you 1.4 times 10 raised to the power 11 Newton meter. So the torque is 1.4 times 10 raised to power minus 11. Power of 11 right there. Part C. The distance between the centers of spheres S and L is 6 centimeters, as shown in the diagram. The mass of sphere S is 7.5 grams. The mass of sphere L is 1.3 kilogram. Right? Of course, you need to change this one into kilogram. This is going to be divided by 1,000. You'll get 0.075 kilograms. Okay. By equating the torque in B part 2 to the moment about the thread produced by the gravitational attraction between the spheres, calculate the value for gravitational constant, value for G. Of course, we know that our gravitational force is given by this equation of x squared, and we know that moment is equals to force times distance. Okay, so we are equating the torque in B part 2 and the moment about the thread produced by gravitational attraction, right? So if we are to substitute the value of F here, then we'll get GMM times D upon x squared, right? Then of course we know if we do the correct substitution, then we say G times mass, which is here 1.3 times 7.5. Of course, when you convert this one into standard form, it will be 7.5 times 10 raised to power minus 3. So 7.5 times 10 raised to power minus 3. Power minus 3 times distance, which we are given is 8 centimeters. So 8 times 10 raised to power minus 2. And all over this, the distance between the two is 6 centimeters. So 6 times 10 raised to power minus 2. And this is squared, as you can see there. We square that. Now, let's equate now. Equating. We are supposed to equate the torque to the moment. Of course, the torque, we know it is force times D. And this we had gotten it to be 1.4 times 10 raised to power minus 11. So let's equate this to the moment. So we need to calculate G. So it will be G times 1.3 times 7.5 times 10 raised to power minus 3 times 8 times 10 raised to power minus 2. All of this is divided by 6 times 10 raised to power minus 2 squared, and this is equal to 1.4 times 10 raised to power minus 11. And therefore, G, which we are calculating, will be equal to 1.4 times 10 raised to power minus 11 times 6 times 10 raised to power minus 2. This is squared. All over this is 1.3 times 7.5 times 8 raised to power minus 2. And of course, when you do your correct evaluation, you'll find that G is equals to 6.46 times 10 to the power of minus 11. Of course, the units will be newtons meter squared per kilogram squared, which is given right here. So this is going to be approximately 6.5 times 10 to the power 11. Of course, this, when you round off, this will be 6.5 times 10 to the power 11. Very good. We've shown that that is G. Calculated G there, gravitational constant. Lastly, part 2 of this question. Suggest why the total force between the spheres may not be equal to the force calculated using Newton's law of gravitation. Of course, the law only applies to point masses. We know that. That is, the Newton's law of gravitation applies to point masses. And L and S are not point masses because they are not isolated. So that's why the total force between the spheres may not be equal to the force calculated. You see, Newton's. You are suggesting why you see Newton's laws of gravitation. So we know that the law, that is the Newton's law of gravitation, only applies to point masses. Applies to point masses. Point masses are masses that are not under any influence of any other than those two, point masses and S, and L and S. L, that is spheres L and spheres S, are not point masses, are not point masses. The reason is they are not isolated. They are not isolated. They are not isolated. They are still under influence of gravity. That's it. Number 3. Number 3 is from variant 4.2 of February-March 2019, and this was question number 1. Define A1. Define gravitational potential at a point. Of course, this is gravitational potential at a point is work done. This is work done per unit mass. Per unit mass in bringing that mass from infinite to that point. From infinite or from infinity to that point. Use your answer in part 1 to explain why the gravitational potential energy, gravitational potential near an isolated mass is always negative, right? So gravitational force is always attractive, we know that, but we are talking about gravitational potential. So you can start by state that gravitational force is an attractive force, is always attractive. Okay, and therefore, how do you call it? Gravitational potential. Gravitational potential at infinity is 0. At infinity is 0. So basically what this means that a gravitational potential reduces. Gravitational potential will reduces from 0. Of course, 0 is the greatest potential. From 0, from infinity, as the masses approach another mass, as the masses approach. Of course, this will be in the direction. This will be in the direction of the gravitational field. Gravitational field. Hope that's clear. A spherical planet has a mass of this 6 times 10 raised to power 24, and that's a radius of 6.4 times 10 raised to power 6 meters. The planet may be assumed to be isolated in space. That's key. Assumed isolated with masses concentrated at its center. A satellite of mass 340 kg is in a circular orbit around the planet at a height of this above the surface. For the satellite, show that its orbital speed is this. I need to show the orbital speed is that, and of course, since it is moving in circular motion, then it is acted by centripetal force, and centripetal force is always due to gravitational force. So we know that the equation for centripetal force is mv squared over r, and so I say that this centripetal force is due to gravitational force, which is given by that. So of course this m and this m will cancel. One r will cancel to get one r there, to remain with r. And therefore the equation will be v squared is equals to gm over r, and v therefore will be square root of gm over r. Okay, this is the square root of all that. And we know what is, we know g, so we're calculating v now, and we know that g is 6.67 times 10 raised to the power minus 11 times the mass here, which is given to be 6 times 10 raised to power 24, and this is the radius or the distance between the sender. If this is the planet, and this is the orbit around which the satellite is orbiting, the r we are describing here is this distance here. Okay, the distance there will be the sum of the radius of the planet, 6.4, plus the distance from the surface to the orbit, which is this. So then will be 6.4 times 10 raised to power 6 plus this is 10 raised to power 5. You can write it 0.9 times 10 raised to power 6 to make it power 6 there. So all of this, when you evaluate it, you find the square root, and the square root will be equivalent to 7.4 times 10 raised to power 3 meters per second, which is the same as that one right there. Part 2, calculate its gravitational potential energy. Of course, gravitational potential energy is equals to g m over r. G is 6.67 times 10 to the power minus 11, times 6 10 raised to power 24 times 340, which is the mass of the satellite, and the radius is what you have r is what you have calculated up there, 6.4 times 10 raised to power 6 plus 0.9 times 10 raised to power 6. When you do correct calculation, you will get the gravitational potential energy. Of course, this should be less than 0 because 0 is at infinite and is the maximum gravitational potential energy. And this one, when you calculate it, is 1.9 times 10 raised to power minus 10. So you need to include the negative to show that the energy is less than 0. Of course, you don't need to write the units are provided in there. C. Rockets on the satellites are fired at a short time. Okay, this is supposed to propel the rocket. The satellite's orbit is now closer to the surface of the planet. The satellite's orbit is now closer to the surface of the planet. State and explain the change, if any, in the kinetic energy of the satellite. We have said that V squared is equals to gm over r, but G and M are constants. From these equations are constants. So the speed of the satellite will depend on the radius. So V squared is inversely proportional to the distance from the center of the satellite to the height at which it orbits. So this means that as r, of course, the r I'm talking about here is this one, the distance from the center of the satellite to the orbit. That is the r I'm talking about. So as r decreases, as the satellite comes closer to the surface of the Earth, it means that V will increase. V squared increases, the speed increases. We are supposed to state and explain the change, if any, and therefore the change here of kinetic energy. So basically, kinetic energy will increase. Kinetic energy, EK, will increase. EK will increase. And the explanation is that right there. We know that kinetic energy is equals to half mv squared. So as v squared increases, so kinetic energy also will go up, will increase. That is it, guys, for these gravitational field questions. Visit Solved Papers for more questions, for more topical questions. You'll also get a solved past paper in this site, solvedpapers.co.uk. Do as much practice as you can. You need my help, you know where to get me, spacacademy.co.uk. Hopefully I'll see you in my next video. Cheers.